Hello and welcome to this Chauvin Arnoux webinar. In this webinar, we're going to be taking a closer look at advanced insulation resistance testing techniques. My name's Kevin Smith. I'm Business Development and Marketing Manager here at Chauvin Arnoux in the UK, and I'm going to be your presenter during this webinar. If you'd like to discuss any of the topics raised during the webinar, you can connect with me via LinkedIn. So for those of you who don't know anything about Chauvin Arnoux, we were founded in Paris in 1893 by Raphael Chauvin and René Arnoux. Chauvin Arnoux has played a major role in the history of test and measurement. We have a long and prestigious list of inventions, such as the universal tester, which was the ancestor of the multimeter, and also the current clamp. In the 20th century, more than 350 patents and brands were registered by Chauvin Arnoux. To give you an idea of some of the numbers involved, we have an average annual sales revenue of around 100 million euros. We have 10 subsidiaries spread across the world, of which the UK subsidiary is one. We have 900 employees across 7 production sites and 6 R&D departments worldwide. And we're also very proud to say that we spend around 11% of our revenue on research and development, always ensuring that we get the latest and most up-to-date products within our range. So before we get started, there's a few things I want to talk about to help you get the most out of this session. The first one is testing 1, 2, 3. Please take a moment now just to check that you've got your audio levels adjusted correctly, that you can hear the content, and that you've got a good, reliable and stable internet connection. If you do experience severe problems during the webinar, sometimes logging off and back on again will help you correct those. The session today has a duration of approximately 1 hour, and during that session you can use the questions box to ask any questions as we go. We do have staff on standby to answer your questions during the session, so please feel free to type those questions into the question box during the session. Remember to download the presentation handouts. If you go to the go-to toolbar, you'll see there a section called handouts, and in there's a PDF copy of the presentation slides. So no need to write any notes down or remember all of the content. We've already provided you with a PDF copy of the presentation slides. Now at some point after the session, usually a few days after the session, you'll be sent a certificate to say that you attended, and also again maybe a week after the session we will release the video of the session to our website, www.cauk.tv, and also on our YouTube channel. So please keep a lookout for those. And you can also visit those sites to see previous webinars that we've uploaded in the past. So with that said, let's get started. So we've called this webinar session today Advanced Insulation Resistance Testing Techniques. And this is really part 2 of a 2-part webinar series. Last month, we released a webinar which was an introduction to insulation resistance testing. So again, that was really the basics and introducing you to the subject. Now we're going to build on that content to actually look at a few more advanced testing techniques that you might want to use in your day-to-day work. So we're going to start off with looking at high voltage insulation test applications and the test voltages used. We're then going to look at the causes of insulation degradation and failure. We're going to look at the advanced testing techniques, things like DAR, pi, and DD, and step voltage. And obviously we'll talk all about what these mean, so it does sound a bit sort of jargony at the moment, but we'll explain exactly where they fit in. And then we're going to finish up with having a bit of a look at what actual test equipment we've got available from Chauvin Arnoux that will help you carry out this type of testing. So that's the plan for the webinar today. In this section, we're going to have a look at high voltage insulation testing applications and the test voltages used. In our last webinar, we looked at the testing of typical installations and equipment using test voltages less than or equal to 1000 volts. In this webinar, we will see how voltages above 1000 volts can be used to perform a greater range of tests as part of commissioning and preventative maintenance testing processes. In our last webinar, we also covered the safety precautions relating to insulation testing. Only those competent to do so should perform insulation testing. Our previous webinar is now live on the website and YouTube channel for you to watch again. So this is a very important point on here. Obviously, insulation resistance testing can be dangerous. It can pose a danger to those doing the testing and also those around them. So be very careful and only do this if you are competent to do so. So as we mentioned before, we've already covered a lot of the precautions needed in our previous webinar. So I would go back and watch that as a starting point. But obviously competent is a lot more than just watching a video. So please make sure that you are competent to do so if you are going to carry out this sort of testing. In this webinar, we're going to discuss the theory relating to and test techniques used to perform insulation resistance testing in typical applications such as motors, generators, transformers, and wiring systems. So these are very typical tests that we'd be using maybe in an industrial or a site environment to actually carry out checks maybe as part of commissioning or as part of an ongoing preventative maintenance process. And we are generally talking about things like motors, generators, transformers and wiring systems, but this could equally apply to, insulators in a high voltage system, and it's almost endless the applications that you could use these for. But today we're going to talk about the standard applications, things like motors. We will talk about in quite a lot of detail. So although we're using these applications to as a context for our session today, obviously the amount of insulation resistance testing is a very wide topic. So we'll look at insulation resistance testing, which is a form of non-destructive condition testing. We will not cover breakdown or dielectric strength testing, which is a different subject. So very important. What we're talking about today is non-destructive condition testing. That term non-destructive is very, very important. We're not trying to prove, what voltage we can use to break this equipment, what voltage we can use to get the insulation to flash over under surge conditions and things like this. What we're doing is we're using these high test voltages, this insulation resistance test, to non-destructively test and monitor the condition of insulation. So that's where this differs from something like maybe flash testing or, dielectric strength testing. We're not looking to break it down. We're not looking to put this insulation under so much stress that it may get damaged. We're looking to do non-destructive testing so that it's repetitive and we can continually monitor and compare the conditions over time. Insulation resistance measurement yields a result expressed in That's interesting. Insulation resistance measurement yields a result expressed in kiloohms, megaohms, gigaohms, or in some cases even teraohms. This resistance indicates the quality of the insulation between two conductors. It is particularly useful for monitoring insulation aging during the operating life of electrical equipment and installations. This measurement is performed using an insulation tester, also called a megohm meter. Insulation resistance measurement is based on Ohm's law. By injecting a known DC voltage and then measuring the current flowing, it is simple to determine the value of resistance, which is very high but not infinite. This resistance characterizes the quality of the insulation between two conductors and gives a good indication of the risk of leakage currents flowing. So when we're selecting a test voltage, there's various methods of doing this, and generally, data provided by the manufacturer would be the best way to do this. So if in doubt, always seek out the manufacturer of the motor or the cable or the generator or whatever it is that you're measuring. But there is some standard values taken here that are pretty common, and these are used across a lot of other standards as well, like BS 7671, for example. A lot of these values will be familiar to people who are carrying out those sort of testing. So generally we look at the system voltage or the nominal voltage at which the equipment is going to be working or is going to be rated. And as a basis of that, we then look at the DC test voltage. And there's a balance to be had here, because what we're trying to do is we're trying to put the insulation under, sufficient stress to give it chance to fail, to give it chance to to actually indicate that there is a problem with that insulation. So we need to put it under sufficient stress to be able to detect any weaknesses within the insulation. But what we don't want to do is we don't want to put too much stress under it that's actually going to damage it. Remember, we were saying this is a type of non-destructive condition testing. We're not here to try and break this. We're not putting it under stress to break it down. What we're trying to do is use enough voltage to be able to actually determine its condition without causing damage. So you can see on here for typical circuits, circuits, our 230 volts main circuits, for example, we would generally test somewhere between 250 and 500 volts, and a 500 volt insulation resistance test, as we talked about last time, is very common. But as the circuits start to go up, that's where we need to start using the higher voltages to actually get some information. And we'll also talk about, as we go on, about step voltage testing. And step voltage testing, again, uses that difference in test voltage, that increased test voltage, to actually tell us about the condition of the insulation. So depending on the application that you're working on, depending on the actual type of equipment and its rating, that's where we would actually look at to see what would be a suitable test voltage. So this was taken from an IEEE guide. But again, this is quite common in many standards, and it's always worth looking if you've got equipment that's rated to, certified to a certain standard. Obviously, have a look in that standard to see what test voltage they recommend, and obviously, we'd also recommend consulting the manufacturer. So this is key. This is absolutely key to understanding the types of testing that we're doing when we talk about these advanced testing techniques. And what we need to understand is that there's actually, when we're carrying out an insulation resistance test, there's actually 3 types of current that flow within that insulation. And what we're trying to do is we're trying to differentiate between these types of current, because 2 of these types of current are temporary and they will eventually go to a steady state. And the third one is the actual current that we're trying to measure, the actual leakage current. So when we look at this, the first one, and this is represented by the blue line on the chart here, is the capacitive charging. So whatever insulation we've got 2 conductors and we've got a dielectric material, we've got an insulator in between those, and that effectively describes a capacitor. So generally when we're testing insulation, it will have a level of capacitance. Now this depends on the type of equipment. If we've got a very long cable or a very short cable, if we've got very big equipment, small equipment, the capacitance will vary. But what you will see is that when we first apply the test voltage, we will get a current flow. And that current flow is going to effectively charge up that capacitor. It's charging that capacitance. So initially we'll get a current flow, but once that capacitance is charged up, then again that current basically goes to 0, or certainly becomes negligible. So we have this charging current. So you can see there the blue line when we first start off, probably for under a second, probably less than a second, we will see this charging current. Now, obviously, if we took the test readings or we monitored the test readings during that time, we would get a changing value of insulation resistance, and it wouldn't be the true value of insulation resistance. So we need to make sure that we've applied the charging current for long enough, the test current for long enough that we've got past that point at which the capacitance within the circuit is charging up. We've also got what's called the absorption current or the polarization current. And what this is a sort of phenomenon that when you actually apply a DC test voltage, or suitably high DC test voltage, to this dielectric, to this insulation, what happens is there is a certain current flow, and this takes time. And this is the molecules within the insulation aligning themselves to the polarity of the test voltage. So obviously using a DC test voltage, there will be a positive and a negative. When we actually apply it within that insulation, there will be a random alignment generally of all of these molecules within the equipment. When we actually place the insulation under test, there is a period of time where the insulation actually orientates itself and polarizes itself to that application of positive and negative. So all of the molecules there are aligning themselves with that. That again takes a period of time. So you'll see there on the red line, you'll see that we're actually seeing over a period of time this polarization effect, this absorption of as the material aligns itself to the test voltage. So that again is a current flow, but this isn't due to anything to do with the quality of the insulation. This is just a fact. It's based on the insulation, and it does change depending on what insulation medium you've got. So what material you're using, this will take longer or less time, and again, the thickness of the insulation and the cross-sectional area and all these things will affect this. But it isn't to do with the condition of the insulation as such. This is just a fact of any insulation, whether it's new, old, damaged or not. You will have this absorption current that will flow for a period of time. So again, this is why it's important for us to apply the test voltage for a suitably long period of time to allow this to deteriorate to where it's not affecting the overall readings. Now, the one that we are actually looking for, the current that we are actually trying to identify, is the conduction current or the leakage current. So this is the current that is being conducted through the insulation. So this is actually our conduction current. So when we apply the test voltage, what we will see is after, again, a very short period of time, this will go to a steady state, and this will be our conduction current. And this is the conduction current that we use then, as we said, with Ohm's law. We know the test voltage, we know what current's flowing. We can then use that current to calculate the insulation resistance, and it will go to a steady state. So when we're carrying out these tests, we need to be aware that we have to apply it for a suitable time to allow for the capacitive charging, for the polarization, and for the conduction current or the leakage current to get to a steady state. And at that point, then we can take the readings. Now, normally with most circuits, when we're dealing with sort of, typical domestic installation, or we're doing pat testing or whatever, generally these things happen very quickly. And potentially we're not applying a massive voltage, so it's not, they're not charging up to a massive voltage. They're only going to charge up, say, 500 volts or whatever it is. So a lot of these things happen very quickly. So when we looked at our last webinar, generally we're talking about a lot of spot testing. We connect it up, we take a reading, pretty much look at the reading, that reading's stable, and away we go. But when we're talking about, bigger insulation, we're talking about higher test voltages, this is where these things do come into effect, and we have to be aware of them. But the good thing is, as you'll see when we actually get into the testing techniques, we can use these to our advantage. We can actually use these charging currents and use the fact that this is a known state, and we can actually use this to tell us about the state of the insulation as well, which is really good. And when we start looking at testing techniques, you'll see how we actually use this. The fact that it starts off and the currents are changing, and then we get to a steady state, and we can use that to actually tell us a bit more about the condition of the insulation. So just be aware when we're carrying out these tests, this is why we can't just connect it up and say, right, that's your reading. We do have to leave these for a period of time and to actually get a reliable reading of the actual leakage that we want to know and the actual insulation resistance. So there's two further factors that must be considered for consistent measurement. First one is temperature. Now, temperature of the insulation makes a huge difference. And this is quite interesting actually, because this was something I learned during this installation. This is opposite. The relationship between insulation resistance and temperature is actually opposite to what you'd expect from a conductor. So generally with a conductor, the higher the temperature, the higher the resistance. So as the temperature increases, the resistance increases, and that's what we were always taught, day one, week one on any electrician's course, when you start learning about, Ohm's law and these sort of things and the relationship between conductor resistance and temperature. We were always taught that basically as you heat up a conductor, the resistance goes up. Now with insulators, we're talking the opposite end of the scale. A conductor has a very low resistance. It allows electrons to flow through it very easily. When we get up to insulation resistance, we're talking at the opposite end of the scale. These electrons are really bound into that structure. And insulators don't work in the same way as a conductor. What happens in an insulator is when we increase the temperature in an insulator, the insulation resistance actually decreases. So that's a big change. The insulation resistance decreases as the temperature goes up. And it actually makes a big difference. You know, a 10-degree change in insulation temperature can actually halve the insulation resistance. So it actually makes a big difference to the measured insulation resistance. So we have to be aware of that. And what we can do is we can either carry out the testing at a set temperature. So we measure the temperature of the insulation during test. So it might be 20 degrees or whatever it is. And we always carry out the test at that value so we can compare these readings over time. Or what we can do is we can actually measure the resistance and then correct using a correction table. Or actually with some of the Chauvin Arnoux products, you can actually connect a temperature probe to the insulation and the temperature correction will actually be carried out automatically by the instrument, which is obviously an easier option. But we need to take temperature into effect when we're actually trying to get a reliable insulation resistance reading over time. So we need to make sure we're either at a constant temperature or that we've corrected for temperature, because temperature does make a big difference to insulation resistance. Another thing that also makes a difference is humidity. So humidity, we could either be talking about the humidity of the air or actually even the humidity within the insulation. So if there's moisture within the insulation, again, you know, this can create a problem. So it may not be that there's actually a problem with the insulation. It may just be that it's been in a damp environment, or maybe it's been cleaned, it's been washed. It could have been exposed to water. There could be all sorts of things where it may need to have dried out at a period of time. So sometimes when we actually carry out a test, we may find that there's a problem with the insulation resistance due to humidity, but actually that's just a temporary effect. And once it's actually been dried out properly, then it's okay again. So it may be something that's actually reversible. The other thing is the humidity in the air. So if we've got humidity in the air, particularly if the humidity and the temperature is below the dew point, we can actually get humidity even on the surface of the insulation, or we can get humidity that's actually affecting those results. So again, it's useful to know the humidity and the temperature and be able to correct for those and take those into effect. Obviously, we'd like to carry out the insulation in a sort of dry environment, the insulation resistance testing in a dry environment if we can, and obviously insulation in a dry state. So just be aware there's two factors there that really can make a big difference to the insulation resistance. If you look at a graph there on the right hand side, what we're sort of plotting here is obviously a preventative maintenance cycle where we've actually been carrying out these tests over time. And what happens is, what this is illustrating here is we've obviously carried out tests and we've noticed there that there is a steady drop off in insulation resistance. That's then been followed by, at point B there, we've actually followed by a catastrophic dropout. So what we've seen is a gradual deterioration over time, which potentially we should have identified as part of our preventative maintenance and kept an eye on. And that's then led to a catastrophic drop in insulation, at which point something's had to be done there at B. It's had to be a repair, or you know, something's actually have to be replaced. And then we put the back into service, and we continue at point C there to monitor that insulation resistance over time, ensuring that it's, you know, it stays within the parameters that we'd expect and we haven't seen any deterioration there. So by plotting insulation resistance over time, we can actually check what's going on with the condition of the insulation. But again, as we're taking these readings, as we said, we want a constant temperature. We need to correct for temperature. And also we need to be aware of the impact that humidity is having on that as well. Because what we don't want is the fact that actually we're not seeing a real deterioration. All we're seeing is a change in temperature at the time of test. So to be able to get those results, we need to be in control of our environment, which is very, very important. So now let's take a closer look at the causes of insulation degradation and failure. So there's 5 key reasons that insulation fails. In fact, there's probably more than 5 reasons, but all of them can be broken down into these 5 topics. So all of the reasons will fit under one of these 5 groups. So the first is electrical stresses, and these mainly come in the form of overvoltages, so voltage surges and spikes, or undervoltages, so this is things like voltage dips. Mechanical stresses. So mechanical stresses are to do with starting up and shutting down. So that could put torsional stress and things like that, mechanical stress within the windings and within the insulation. Also, balancing issues can actually cause a lot of mechanical stresses. You can imagine that if it's vibrating or if the thing's not actually aligned correctly, these again can cause mechanical stresses on the insulation. Chemical stresses, again, these come in many forms, but this could be the proximity of chemicals, oils, or maybe even corrosive vapors, dust. All of these things can actually deteriorate insulation. Stress is linked to temperature variations. So again, we can have things like thermal cycling. So when insulation heats up, cools down, it can cause it to degrade. But we can also get heating within the motor itself. So maybe if the motor's overloaded, again, this is another form of electrical stress, but the temperature effect of that can actually affect the insulation. So there's a lot of reasons within there for sort of temperature related stress on insulation. And the final one is environmental contaminants. So this could be stuff like the buildup of mold. This could be deposits of, dust, oil, chemicals, dirt, all of these sort of contaminants that actually get into the insulation. So this is slightly different from chemical stresses. Chemical stresses are things that are actually sort of eating away at the insulation and causing stress, whereas contamination is things that are actually getting soaked into or getting actually impregnated into the insulation, causing it not to be pure insulation. It's got other things in there. We talked about moisture. Again, that was another typical form of environmental contamination that we may come across. So again, there's a lot of reasons why insulation should fail. And obviously, common sense dictates that keeping your motor, dust-free, dry, clean, away from any oils or contaminants or coolants and things like that. All of those things are obviously good practice if you want to see your insulation last and, a long life for your motor. So again, in any preventative maintenance system, we try to keep away from that. Now we've got a pie chart here that shows the sort of typical failure modes effectively for a motor. And you'll notice that the main part on this, the biggest chunk there, 43%, is external contamination. So again, this is the mold, this is the dust, this is the grease, this is all of these things getting into the motor and getting into the insulation. This is what's causing a lot of failures. 25%, next one down, is overloads. So the motor being overloaded. So if the motor isn't specified correctly, or we're actually putting too much load on it, we're using it for something it's not meant to do, that obviously adds to all of these other stresses. It adds to the starting stresses, the mechanical stresses. It adds to the temperature variations. It's a form of electrical stress as well. So again, this is another reason that these things fail. So you can see there 43% for contamination, 25% for overload, 12% then followed up by mechanical faults. So some form of physical mechanical fault within the motor, again, allows for 12%. And then when we finish up, we've got face-to-face faults. That could be something like an overvoltage potentially. Insulant deterioration, so the insulation actually deteriorating. Now, we're pretty good at selecting insulation and using insulation materials that don't deteriorate that much. So no surprise, it's only 5%, and then other things is another 5%. So you can see if you want to look at, how to keep your motors healthy, how to keep your motors, in service and not failing, look at external contamination, look at keeping these things clean, properly specify your motors, don't overload them. Try and avoid mechanical faults, preventative maintenance, keeping on top of these things, checking the bearings and alignment and balancing and all this sort of stuff. And then realistically, we will deal with a lot of the stuff that's in there. So there's all of these reasons why insulation could fail. And if we actually go into the main one, this external contamination, a little bit more in this next slide, we've actually got a little bit more detail on where all this comes from. So if we look at that 43%, if we actually go into that and start and have a bit more of a look in detail on that, you can see most of that is oils and grease. So again, a lot of times motors are going to be used in this environment where there's a lot of oil and grease about. Again, that's allowing for a lot of that contamination. Mold, that's a surprising one really, mold, but mold growth actually is a big one. Dust and particles, and again, particularly if that's a conductive dust, so you've got like metal dust or something like that in there. Again, in fabrication environments and factories, that can be quite common that you've got a lot of conductive dust in there, and obviously other chemicals that are about as part of that process. So it is important to understand, the modes that these types of equipment or the insulation can fail by, and then obviously decrease, just try and remove those as much as possible. If we can understand it, we can put mitigation in place, and as part of our preventative maintenance, we can clean these things, we can try and remove these things. So when we're actually carrying out insulation resistance testing, this is just a way of us non-destructively checking the condition of the insulation. But again, we're only measuring this thing. So the it's not an insulation resistance test isn't going to stop these things from happening. What's going to protect your insulation and ensure less failures is actually minimizing these factors that we've just looked at on these previous two slides. So insulation resistance testing is a method of checking the condition of the insulation over time. But if we do actually identify insulation resistance problems, one, it may be too late. But two, we actually need to look at the root causes, which again are these things that we've talked about on these slides. Now let's get into the actual meat of this session. Let's have a look at the advanced insulation testing techniques. So when we looked at the last webinar, we looked at effectively the simplest and most basic method of doing this, which is effectively a spot measurement. This is carrying out a spot measurement. We're just going to check the insulation straight away and see what it's like. Now, previously, when we were talking about doing spot measurements, we were pretty much doing that test there and then straight away. Now, we've learned actually, if we're talking about bigger insulation, we're talking about higher test voltages, that actually doing a spot test straight away isn't really a good idea, because the insulation resistance will change over time due to the capacitance and the absorption currents that need to neutralize. So what we suggest is, if we're actually carrying out a short time or a spot reading, that we actually allow maybe 30 seconds or 60 seconds before actually carrying out the test. And a lot of the testers that we provide at Chauvin Arnoux will actually have a timed feature in there, so that they'll actually have a timer and they'll let you, carry out the test, and then it will take the result after a set period of time. So what that time is does depend on the insulation that you're using, the test voltage and the characteristics. But the key to this is you need to allow enough time for that insulation resistance reading to stabilize. If you're looking at the display and the insulation resistance reading is still changing, it's still going up or going down, you need to have a look at that and think, actually, I need to apply a bit more time to this. So don't be afraid to apply this for, say, 60 seconds before you actually do the test. Does it appear to be stable? If not, then potentially you need to allow more time to get that stable reading. So just be aware that we can just carry out spot tests, but we do need to allow time for that reading to stabilize. Now, the other thing we mentioned about spot tests is when we're comparing spot tests, we need to be aware of the temperature at which the insulation was when the test was carried out, and the humidity of the environment and of the insulation when we did that. So it's fine if we are just carrying out that test at the same time, same humidity every time, then we've got comparable results. But if not, we do need to find out what they are and carry out corrections so we can compare over time. We don't want to be just confused with our results thinking the insulation's deteriorating when it's just a change in temperature. Now, when we start looking at more advanced techniques now, we're actually looking at our timed ratio methods. Now, these are great methods to apply because they are ratios. So it's just one value divided by another value. And what that means is, because it's a ratio, there's no units. And because there's no units in there, we don't have to worry about temperature compensation, because we're just comparing one reading divided by another. So it gives us a ratio. So the ratio is irrespective of temperature. So that's one thing why these are good tests. So these tests rely on the fact we talked about this change in insulation resistance over time because of the charging and, as we'll look at later on, discharging rate of the changing current. So these methods use the fact that in good quality insulation, the resistance should increase during the test period. This is because the effect of the leakage current is small compared to that of the capacitive and absorption currents. So if you think about this, if our leakage current is small, the effect, or the perceived effect, of capacitive and absorption currents is more, because it's small compared to those. Now, in poor insulation, the high leakage current outweighs the other currents, and little change is seen over time. So if you test straight away and actually the insulation pretty much seems to be the same value all the way through, that's generally because you've got a very high leakage current, and because you've got a high leakage current, you can't really see the effect of the capacitive and absorption currents because they're so small compared to the size of that high leakage current. So by actually carrying out this ratio test, we're actually using the fact that if we've got a small leakage current, then we should see a greater effect of the capacitive and absorption currents. Whereas if we've got a high leakage current, so in which case poor insulation, then we won't see much of a change over time. Now, the first test that we're going to look at here is the dielectric absorption ratio test, or DAR, or DAR test. Now, as we said, this is a ratio. So we've got two readings are taken. The first one is taken at 30 seconds after the start of the test, and the second reading is taken at 60 seconds. So the DAR is the ratio of one to the other, and as we said before, is independent of temperature. So if you can see on here, we take the resistance reading at 60 seconds, we divide that by the resistance reading at 30 seconds, and then we get a value. And what we can do then is we can apply that value using this table at the bottom here. So if it's less than 1.25, the insulation is considered to be insufficient. If it's less than 1.6, it's considered to be okay. And if it's greater than 1.6, it's considered to be excellent. So this is just a simple ratio test, 30 seconds versus 60 seconds. And we just look at those values, and based on the number that we get, we divide one by the other. And then we can use this to actually determine whether that insulation is, as far as we can tell, in good condition. Now, with the dielectric absorption ratio test, the DAR test, remember this is taking values at 30 seconds and 60 seconds. That may not be long enough for some insulation. If we're talking about, sort of chunkier insulation, higher test voltages, then maybe the DAR test probably might not be long enough for you to actually see what happens. You can always carry out the test and you can see what it tells you. But again, sometimes you may need to go to a longer period of test to actually get a better idea. And that's where the next test comes in, which is the polarization index test, or PI test, or pi test. So again, this is taking two readings. So we take two readings, but this time the first one is taken at 1 minute, and then the second one is taken at 10 minutes. So we're actually applying the test for a full 10 minutes here. And this gives us excellent time for that insulation, that polarization to take place, and for us to get a key idea of what's going on. So sometimes, like we said, for higher test voltages or for bigger installations, this may be a good idea to actually try this. Again, you can do both. You could try a DAR test. If you're not convinced 100% with that, go for a polarization index test. These aren't exclusive. You don't have to just pick one. You can carry out these tests and see the difference, see the effect of what's going on with this. So again, this is a ratio. So we divide the 10-minute reading by the 1 minute reading, and that will give us a value. So if we get a value of less than 2, it suggests a problem with the insulation. Anywhere between 2 and 4, we would say is probably good insulation. And anything over 4, we're saying is excellent insulation. Now, again, with any of these values, it is a rough rule of thumb. It depends on the insulation. It depends on the type of equipment you're measuring, the test voltage, all sorts of things. But these do give you a good indication of what's going on. And like I say, you can apply these tests, in multiple different ways to just get an idea of the picture that's going on there. So you could do a DAR test and a pi test and compare both values. But these are quite reliable tests that are carried out to check the condition of the insulation. And generally with our insulation resistance testers from Chauvin Arnoux, these will be automatically in there. So you can just select to do a DAR test, to do a pi test, and it will automatically carry those tests out and do the calculation for you. So it's quite interesting. You don't have to do these manually, don't have to sit there with a stopwatch and check these things, although you can do if you want with a basic tester. But a lot of times this is just built in. This is just a feature that's built in within the tester. And as long as you understand, what the numbers mean and how to do it, it's very, very easy to perform. Now, another type of ratio test is a dielectric discharge test, or DD test. Now, this is very different because what we're looking at, this is almost the opposite to the DAR and the pi test, which they were looking at measurements during the charging of the insulation. So we'd apply the test and actually charge it up. The dielectric discharge test, as the name suggests, actually talks about the discharge period. So once we've removed the test voltage, what then happens, you know, to the voltage afterwards? How does it deteriorate? How does it fall? So the dielectric discharge test looks at the test voltage, it looks at the current, and obviously over a period of time. So as it says there, the current after 1 minute. So it's looking at over a period of time, what's the current fallen to? What is the voltage across the insulation? What's that drop down to? What's the capacitance? And then as a result of all of that, what it comes out with a value. And then that value, that ratio, then we can use to actually check the condition of the insulation. So if it's greater than 7, it's considered to be bad. 4 to 7 is poor. 2 to 4, questionable. And anything under 2 is okay. So this is a different way of doing it. This is looking at the other way. So we've done a charging cycle with a DAR or a pi test. And then this is actually the opposite. This is the discharge end of the curve to see what's happening when we discharge it. And it's a similar process, but it's just a different way. I believe this is better for detecting certain faults, particularly within multi-layered insulation, I believe. So there is applications why this would be better than others. And as I've said before, sometimes people will apply, you know, all of the tests or a couple of the tests together just to actually collate the insulation to make sure that they're all giving a good reading, rather than sort of a lower reading on one where you're getting good readings on others, and that might indicate something that you need to investigate further, shall we say. So I say these aren't exclusive. This is a menu effectively of tests. You can pick which test suits the application that you're dealing with, and if you're not sure about the results from one test, you can also apply other tests and, you know, use those to inform your picture of the insulation and make any engineering decisions over the suitability or not of that piece of equipment. Now, the next test we're going to look at is slightly different. This is the step voltage test method. So advanced testers like the CA6549 shown here can perform the step voltage test automatically. But it is possible to perform this test manually on other testers with a wide range of selectable test voltages. The step voltage test works on the principle that in good insulation, the resistance should be constant irrespective of the test voltage. So if we carry out the test at 500 volts, we should get the same reading as if we carry out at 1000 volts or 2500 volts. The insulation should be about the same, the resistance should be about the same. So by performing an insulation resistance test at a low voltage, say 500 volts, and then repeating the test at 2500 volts, if the insulation resistance drops between the two readings, then it's likely that there is an insulation problem. If the two readings are substantially the same, then the insulation is likely to be in good condition. So this is a relatively recent test. This is a sort of test that you know, has come about relatively recently, and they've looked into it and they've done research, and they've found that actually if you are getting a difference between the tests, that should indicate that there is actually a problem potentially with your insulation. So it's important that the two voltages selected are suitably far apart to observe the effect. A ratio of 5 times is suggested. So when I mentioned on the previous slide, we were talking about, you know, doing a test at 500 volts and 2500 volts. Again, that's suitably far apart, this 5 times ratio, for you to be able to observe the effect. Now, you could do a step voltage test at 500 volts and 1000 volts, and if there was a difference, again, that may indicate that there's a problem. But in a lot of cases, that wouldn't be enough of a change for you to see any real notable difference. The higher test voltage should be below the level at which damage could occur to the insulation. And in some of the guidance that we've got, it talks about 2 times the rated voltage plus 1000 volts. So quite often when we're looking at flash testing and we're looking at dielectric strength testing, particularly in AC systems, They generally recommend this voltage of around 2 times the rated voltage plus 1,000 volts is generally where they'd start carrying out those sort of dielectric strength tests at. So we would suggest, as a rule of thumb, trying to keep below that if you can. But obviously it just depends the type of equipment you've got, what it's rated for. And as we've always said, you know, the manufacturer is the best person to give guidance on that, to the point where they think, you know, insulation could be damaged by carrying out these tests. So just be careful, you know, don't go, right, well, I'm going to test at 1,000 volts and 5,000 volts, you know, and the equipment's only rated for, say, 100 volts or something like that. Because potentially you could obviously damage the insulation by doing that. So a difference in the readings of 25% or more is considered to show insulation deterioration. So, you know, we're not just looking for tiny little changes. We're looking at something like about 25%, you know, a quarter of the reading or more would indicate that potentially there is a problem with the insulation if we're doing a step voltage test. Now, as we've said, with some of our more advanced testers like the 6549 that's here, these will automatically apply that test. So you just select the step voltage test, you set the steps, you set what you actually want to carry out, you know, start voltage, stop voltage, all the steps in between, and it will carry that out for you and it will actually record those results there. Or, as I say, you can just do this manually by carrying out like a 500 volt test and a 2500 volt test and actually look at the difference yourself from that side of things. Another important item for us to talk about is the use of the guard terminal. A majority of the higher rated insulation resistance testers from Chauvin Arnoux have another terminal on them called the guard terminal. And this is a really useful function. It's often misunderstood by people, and quite often people, you know, don't use it, aren't aware of where it fits in. And this is really important when measuring high insulation resistance values more than 1 gigaohm. The accuracy of the measurements may be affected by leakage currents flowing on the surface of the material. So not through the insulation, which is what we're trying to measure. We're trying to measure the insulation. This is almost leaking around the insulation. So again, you may get false readings. You may get, you know, readings that appear lower than you were expecting, and that might lead you to think that equipment is damaged or faulty, when actually it is just surface leakage currents. So in order to eliminate the surface leakage current, some insulation resistance testers include a third terminal called the guard terminal. So you can see here a diagram of how we use the guard terminal. So what we've actually got is we've got an insulation resistance test carried out here on a cable. And what we're worried about is actually the insulation between the cores and the braiding on the outside. Across the surface where we've actually got the cables exposed at the end, we could get surface leakage. And that surface leakage would basically cause problems for us. So by connecting the guard terminal, you can see the blue terminal here. And what we've actually done is wrap some wire around the insulation to allow contact between the insulation and the guard terminal. So we've wrapped wire around the insulation on those surface paths. And we've connected that back using the blue cables, as you can see on here, to the G terminal, the guard terminal within the tester. And by connecting the guard terminal, the surface leakage can be effectively nulled from the readings. So what that does, it offers that leakage current a separate path back, which is omitted from the actual test that we're carrying out, and it effectively nulls that out. So if we've got any of these surface paths where we're worried about surface conduction, we can use the guard terminal, and we can connect the guard terminal to that point, and it effectively nulls out any of those surface leakage currents that would affect our readings and gives us a pure reading through the insulation, not around it. So the use of the guard terminal is really, really important, and particularly when we're testing certain types of equipment where the surface leakage could cause problems. Again, using the guard terminal will just allow you to increase the accuracy of your measurements. And now to finish up, we're going to have a look at what products are available from Chauvin Arnoux to actually test equipment greater than 1,000 volts. So really, within the range, we've got our 5,000 volt testers, and we've actually got 4 5,000 volt or 5 kV testers within the range. We've got the 6505, 6545, 6547, and the top of the range 6549. Now, depending on which tester we talk about, the there's obviously different specs in there, and I'd encourage anybody who's interested in looking at these to actually have a look on our website, and you can actually see the differences between the models, because there's quite a few differences. Obviously, you can imagine when having 4 models there's quite a few differences in here. Most of what I'm talking about on here is the specs for the top of the range 6549. But obviously there is a lot of crossover between the models. So if you're interested in these, obviously you can get in touch with us. We'd be more than happy to talk with you about it or give you a demonstration. But if you have a look on the product website, you'll be able to actually, get a better idea of which products fit in there. But generally with these products, we've got test voltages, and usually the test voltages are selectable, anywhere between 40 volts all the way up to over 5,000 volts there. And we've got a measurement range anywhere from 10 kilo ohms, so quite low in the terms of insulation resistance, all the way up to 10 tera ohms, really, really high insulation resistances. As I spoke about before, we've got the ability to do the pi, dar, and dielectric discharge test, the DD tests. But these are automatic. It's automatically calculated, so you don't have to do this manually. They're automatically calculated for you. And we can also do the step voltage test on the 6549. We can actually perform automatically the step voltage test. Now you'll see on these products as well, on some of these products, you've got the ability to actually connect on a temperature probe. And if you connect on the temperature probe, you can actually then correct automatically for temperature as well. Now, a few things we've got also available. Again, these generally tend to be on the higher end, the 6549 products, but you've actually got the ability to graph the resistance over time. Now, with some of the products, that's via the software, but on the 6549, you can actually see on the screen, it will actually plot on the screen a graph of insulation resistance over time for you, which is really useful when you're carrying out the test, and particularly if you're in the field. You don't have to download those results to a laptop and have a look at that. You can physically see that curve on the screen of the tester while you're carrying out the test. Now, we can also plot in programmable alarm limits. So if the insulation is below a certain value, it will let you know. It'll give you a warning, so you don't have to look at it specifically and read. You can set up the alarm. So if you're carrying out the test, maybe on a system where you're carrying out a lot of tests, maybe motor windings, and you're sort of carrying out a lot of tests, literally you can set the alarm, listen out for the alarm, and it will tell you, rather than you having to keep an eye on the screen all the time when you're doing it. We've got the ability to store results in the memory, so you can save the results in the memory of the tester and download them afterwards, or review them on the tester afterwards. And you've also got the ability to carry out reports using our data view software. So you can download the results from the tester to the data view software, and you can actually create graphs and create reports within that. Now, common to all these testers in the range, they are very, very rugged. Obviously, they're designed, as we've said here, for site and industrial installation. So because of that, they're in an IP53 rated hard case. So again, these are very, very rugged, really sort of reliable machines to use in industrial environments or out on site environments. They are also battery powered as well. I don't know if I made that clear, but you can actually charge these up and use these battery powered for several days, no problem at all, just carrying out, the range of tests that you're doing. So absolutely great products. These are used, worldwide by loads of people in the industry. They're really well received products, and they're sort of, we really get very good feedback by anybody who uses these products. As you'll know, with any Chauvin Arnoux products, the quality and the usability of these is absolutely brilliant. Now, if we go on to the next two products up in the range, we actually have a 10 kV and 15 kV insulation resistance test as well. So the 10 kV is the 6550 and the 15 kV is the 6555. So these are really top of the range products. These are there for, if you're doing really serious insulation resistance testing on high voltage equipment. And these have got all the features that I've just talked about with the 5 kV products, but they also add a few extras on as well. And obviously the increased test voltage is part of that. So we have variable test voltage, in this case from 40 volts up to 10 or 15 kV. We've got a measurement range from 10 kilo ohms all the way up to, in this case, 30 tera ohms. So right up, we've got the ability to do all the usual stuff, the pi, dar, DD and step voltage test methods. We've also got on-screen graphing, so we can see the graphs on there, and there's a number of different graphs that you can display on this above and beyond what we had previously. We've also got the ability with these products to store up to 80,000 records within the tester, and then we can use our data view software to actually review those and create graphs and reports on the installation that we've got. So again, really, really good quality products, you know, really chunky, really reliable products that you can use out in the field. And we do get, you know, these are very, very popular as well with our customers. So that brings us towards the end of the webinar now. So just in summary, we'll just go back over what we talked about. So this was talking about the advanced testing techniques that we can do with our insulation resistance testers. So we started off with having a look at the actual applications and the test voltages used, and we looked at things like the discharge currents and the absorption currents and all those sort of things, leakage currents. We then had a look at the causes of insulation degradation and failure, so things like mechanical stresses and electrical stresses. We then went on to look in more detail at the actual insulation resistance testing techniques, and we covered things like DAR, pi, DD and step voltage testing. And then we finished up with a bit of a look at what equipment we've got available from Chauvin Arnoux that's rated for greater than 1,000 volts. So thank you for joining us on the webinar. If you like this content, we've actually got more webinars coming. So we're doing a webinar a month. So if you have a look at our website, cauk.tv/webinars, and on there we've got a list of all of our previous webinars that we carried out. And as I said, in about a week's time, we'll get this on the website as well. And we've also got our YouTube channel, and we're trying to promote our YouTube channel at the moment. So please go on there, please subscribe and get notifications, you know, sign up for the notifications so that every time we put a new video up there, you'll get a notification, you can have a look. But I mean, I think this is about the 9th webinar that we've done. We've been doing these for a few months now. So we've got this range of webinars going. So there's loads of content on there already for, you know, low resistance measurements, earth resistance measurements, power quality, all sorts of things that we've already got on here. So we've got a nice suite of webinars on there. They're all similar content to this. They're all similar duration. So again, you know, real great content that we've put together there. So hopefully that's something you can go back and have a look at. Now, just to finish up, obviously, thank you very much for attending this session. It's always great to see such a good turnout on these webinars, and these webinars have been really, really popular. And obviously, you know, that's why we do it, because we like to see the feedback that we're getting from the customers. So remember, before you go to the handout section and download the PDF copy of the presentation. And also keep an eye out in your email box for your certificate that'll be sent out after the event. Normally they go out a few days after we finish the event. We usually have 2 showings of the webinar. So we do 2 sessions, and then a bit after that, they'll be sent out automatically. If you haven't received it, just check your junk folder or something that it hasn't gone in there. But generally, they're sent out automatically, and that's pretty reliable system. We have got the webinars available on demand, as I said, on our website, www.cauk.tv, and we've also got them on our YouTube channel. And if you want more information, we've actually got a load of technical articles and other content available on our website, cauk.tv. So again, we'd urge you to have a look at that and go on there and sign up for the mailing list as well. And then when new content goes on, you'll be informed of that. So thank you very much for listening to the webinar today. If you've got any questions, you can type them into the questions box now, but hopefully we've answered those all through the session as we've gone. And I hope to see you again on another webinar soon. Thank you very much for your time.